Hello there, Mr. Sutton here with the AB Calculus 510 classwork solutions on FTC integral evaluation with polynomials. On this first problem, if f and f, big F and little f, are continuous functions such that derivative of f, big F is little f, then what's the integral from a to b of f of x dx? So they're essentially saying that the antiderivative of f is big F. Nice. So basically, we just have to use our integral evaluation theorem here. If the antiderivative of little f is big F, we can write this as essentially evaluate big F from a to b. So this is just going to be big F of b minus big F of a, which is just answer choice D. For this problem, we have some function f that has a continuous derivative on 0 to c, and we're asking for the integral from 0 to c of f prime of x dx. Well, the antiderivative of f prime is just going to be f, and we're evaluating that from 0 to c. So plugging these in, we just have f of c minus f of 0. And we don't know what either of these actually evaluate to beyond this, so we're just going to have to go with answer choice A. On this problem, we're given the graph of f here, and we're told that the integral from 1 to 3 of f is 2.3, so there's 2.3 units of whatever between 1 and 3 under the curve. And we're told further, essentially, that big F is the antiderivative of f. We want to know big F of 3 minus big F of 0. The key on this one is realizing this is kind of like the end result of an integral. This is essentially taking the integral from 0 to 3 of f of x dx. Right? Because if you took the antiderivative, you'd have big F. You'd be doing big F of 3 minus big F of 0. So that's what we're really doing here, is taking this integral. Okay, well, to take that integral, I need the area under the curve here. I don't know the area all the way, but I do know the area from 1 to 3. So I'm going to split this integral up. I'm going to take the integral from 0 to 1 and just add it to the integral from 1 to 3. And that'll give me this whole integral. Well, what's the integral from 0 to 1? It's just the area from 0 to 1 under this curve. So it's just a rectangle with a base of 1 and a height of 2. So 1 times 2. Plus the integral from 1 to 3 they gave us. They said it was 2.3, and we'll take their word for it. So we've essentially got 2 plus 2.3, which is 4.3. That leaves us with answer choice D. On this problem, we want the integral from 0 to 1 of 3x minus 2 quantity squared. So the easiest way to do this problem is going to be to just expand this. It is possible to basically take the antiderivative of something to the second power and then divide by a tail of 3, and that would also get you there. But I think it's easier if you just expand this. So this is going to be 9x squared, let's see, minus, multiply these together and double it, so that's minus 12x. And then we square the last thing, so that's plus 4. Little dx there. Let's take the antiderivative of this now. So this bumps up to a 3 for the exponent. Dividing by that, we've got 3x to the third. Next, this x bumps up to a power of 2. Dividing by 2, we've got minus 6x squared. And then this will be 4x. All this evaluated from 0 to 1. Now this would be kind of a pain with other numbers, but I'm just going to be doing all this stuff with 1 plugged in, minus all this stuff with 0 plugged in. And this is really nice because 0 just gets rid of everything over in this right bracket. So I'm really just looking at this left bracket, and I'm just multiplying by 1s essentially. So this is just 3 minus 6 plus 4. So this would be, let's see, negative 3 plus 4 is positive 1, which is one of the choices, choice D. Alternatively, if you didn't like my other solution for this particular problem and you want another way to do it without expanding this, maybe something a little more universal in case you have something worse than the second power, the way you could do this is think of all this stuff in parentheses as just something to the second power. Well, the antiderivative for that, I'd have to bump that up to the third power, so 3x minus 2 to the third, and then I'm going to have to divide by some things. I'm going to have to divide by the 3, because that's what I bumped the exponent up to, but I'm also going to have to divide by the tail of this linear inner function, using our little shortcut there. So I'm dividing by a 3 here, and I'm also dividing by this 3, giving me a total of 9 in the denominator. So if you can get around that trickiness, this is another way of doing it. So I've essentially got 3 times 1 and all the rest of this, minus all this stuff with 0 plugged in for x. And the arithmetic works out a little bit differently when you do it this way. This stuff over here, you've got 3 times 2, which is 1, to the third is 1, and we have a 9 here, so that's 1/9, minus, well, over here, this is negative 2 to the third, so that's negative 8 over 9, but we're subtracting, so this is actually going to be plus 8/9. These add up to 1, which is choice D, just a different way to do it. For this one, we've got this integral of x to the 7th plus k equaling 16. We want to know what k is. So to start this one off, I'm just going to use my FTC integral evaluation to expand and evaluate this integral here. I'm going to get some big expression that has a k or 2 in it, and then I'm going to have to use the fact that that equals 16 to figure out what k is. So first things first, antiderivative. So we've got x to the 7th, that bumps up to an 8. Dividing by 8, we've got 1/8 x to the 8th. And then since k is being treated as a constant, since x is the variable of integration, we've got kx as the next thing. We've got that being evaluated from negative 2 to 2, and all of it equaling 16. So that brings our equation a little bit closer to being solvable. Now I'm going to expand the stuff on the left. So I've got all this stuff with 2 plugged in, minus all this stuff with negative 2 plugged in. And all that still equals 16. Going a little bit further, I could figure out what 1/8 times 2 to the 8th is. And I mean, 8's a power of 2, so you could actually use some exponent rules to do this pretty quickly. But I'm just going to be kind of lazy and get rid of these parentheses. So I'm going to write 1/8 2 to the 8th plus 2k. And then over here, I'm going to do minus 1/8 negative 2 to the 8th. And since this is going to be a minus 2k, we're negating it. That becomes a plus 2k over there. Still have 16. Now, the reason I did this is because 2 to the 8th and negative 2 to the 8th, since I have an even exponent, those actually are the same numerically, along with that 1/8 out in front. So this first term and this negative version of that actually end up canceling, which saves me a bunch of time, and I just now have 4k equaling 16 for a k value of 4. Choice D. For this problem, I'm just taking the integral from 1 to 2 of this polynomial. This is a fairly straightforward problem. Just take the antiderivative, plug in 2 and 1, and call it a day. So going from left to right, this bumps up to the 4th power. Dividing by that, we've got 1x to the 4th. Minus, this becomes the 2nd power. 6 over 2 gives us 3x squared from 1 to 2. So we've got all this stuff with 2 plugged in, minus all this stuff with 1 plugged in. And now there's no calculator question, so let's just evaluate it by hand here. This is going to be, let's see, 16 minus 12, which is 4. Over here, we've just got 1 minus 3, so negative 2, but we're subtracting that. So that's 4 plus 2, giving us an answer of 6, which is choice C. This problem is a good example of so easy it's hard. So for this one, they're giving us a g function, that's this quadratic polynomial. They're telling us that f of x and g prime of x are the same thing, and then they want the integral from 1 to 3 of f of x. Well, I'm going to go ahead and replace f of x with g prime of x, because I know a lot more about g than I do about f. So now I need to take the antiderivative of g prime. Well, that's just going to be g. So I've got g being evaluated from 1 to 3, which is to say I have this x squared minus 3x plus 4 expression being evaluated from 1 to 3. So I've got all this stuff with 3 plugged in, minus all this stuff with 1 plugged in. No calculator question, so let's be careful with the arithmetic. So for this first bracket of stuff, this is 9 minus 9 plus 4, so that's just 4. Over here, we've got 1 minus 3, which is negative 2, plus a 4 makes it a positive 2, so we're subtracting 2, giving us an answer of 2, giving us choice C. On this problem, we have a table with values of both f and f prime at selected x values, and we're also told the derivative f prime is continuous from -4 to 1, -1. We want the value of from -4 to -1 of f prime. So antiderivative of f prime is going to just be f. So we're evaluating that from -4 to -1. So I've got f of -1 minus f of -4. Well, what's f of -1? That's just -1.5. And how about f of -4? Well, that's 0.75. So we're going to subtract that. So let's see, that's going to be -2.25, which is answer choice B. And notice that this derivative row was completely useless for this problem. They just threw it in there to throw us off the track. For this problem, we're given that f prime is greater than 0 and the integral of f from 4 to 7 is equal to 0. Based off of this, what could be a table of values for this function? So let's just dissect what they've given us. F prime greater than 0, that's basically saying that our function is increasing for all x values. So that'll help us eliminate some tables here. And this next bit here is saying that the area under the curve between 4 and 7 is 0. Well, that's kind of interesting if f is increasing. I mean, how can you end up with 0 area if your function just keeps going up and acquiring presumably more area as you go? In order for both of these to be true, you must have started below the x-axis and crossed the x-axis to get above it. So you have to cross the x-axis between 4 and 7 because you're essentially adding negative and positive area together to have things cancel out and be 0. And we know that we have to cross the x-axis because this has to be a continuous function. If f prime of x is greater than 0 for all real numbers x, well, that means the derivative exists for all the real numbers x. Anyway, now let's look at our answer choices in light of these. Taking a look at answer choice A, we're definitely increasing, but we're not hitting 0 between 4 and 7. We get it at the end, but we're not crossing it in between. So all this stuff we're adding together would be strictly negative area. Okay, let's see, answer choice B. So for this one, we're increasing, and it looks like we're going to cross 0 between 5 and 7. So far, B is still in the running. How about C? Well, C, we're not increasing all the way. We go up to 6 and then down to 3. D, we're not increasing all the way. And for E, we're increasing, but we don't hit 0 in between 4 and 7. So A and E we can eliminate for not hitting 0 at the right times. C and D we can eliminate because they don't increase. So then choice B is all that's left. For this problem, we're given this function f that's differentiable for all real numbers, and we're given this table of values for f and its derivative. We want to evaluate the integral from 0 to 1.5 of 3f prime x plus 4, and then show the work. All right, well, let's just go ahead and use our integral evaluation theorem. Start with our antiderivative. Antiderivative of 3f prime of x is just going to be 3f of x. Antiderivative of 4, since our variable of integration is x, this is just going to be 4x. And we're doing that from 0 to 1.5. So we have all this stuff with 1.5 plugged in, minus all this stuff with 0 plugged in. And let's see what each of these actually comes out to. So for this left bracket here, f of 1.5 over here in the table, that has a value of -1. So this is 3 times -1, or -3, plus 6, and we'll just leave it there for a minute. Going over to this other one, f of 0 is -7. 3 times that's -21. So we have -21 plus 0, or just simply -21. So we've got, this is going to be 3 plus 21, which comes out to 24.